In this lecture, we'll continue with our analysis on how to implement energy balance via control volume for steady state system. So in few of the previous lectures, we had implemented first law of thermodynamics for closed system. However, most of the engineering systems are flow systems. So we are trying to generalize first law of thermodynamics to these kinds of flow systems. So in the previous lecture, we had dealt with how to implement mass balance. So many of these things are probably elaborated in classes in fluid mechanics, but you should be aware of elementary notions, formula on how to quantitatively discuss mass balance. Okay, so that's what we did in the previous lecture, and we are going to integrate that knowledge with energy balance. So when you start thinking about flow systems, there's one new term which you have not seen in closed systems, which is called flow work. Okay, so flow work, this involves pushing the work done in pushing a fluid into a control volume or outside a control volume. For example, if let's say a fluid is flowing in, okay, so you can imagine the fluid flowing in to be acted upon by an imaginary piston. Okay, so this imaginary piston is also a fluid element. So this piston or the imaginary piston or the fluid element is pushing against this pressure, this mass of fluid. Okay, so the force involved is pressure times this cross-sectional area. That is the force. That is the pressure times the cross-sectional area. And then the work done involves force times distance, right? So this distance actually can be correlated to if you're thinking about, let's say, per unit time. So this distance can be correlated to velocity of the fluid at this cross-section times that unit of time. Okay, so that would give you the length scale. So putting all these things together will give us flow work. So if you look at what this means, this is pressure times a volumetric term, right? So that is going to be, if you express this as specific flow work, that'll be kilojoules per kilogram. All right, so that is the expression for flow work. So you have to understand this clearly. Okay, this is different from other kinds of work which we have seen. When we started this analysis of first law, we looked mostly at PdV term. Okay, that's a boundary work. Then we looked at electrical work, shaft work, and so on. So this new type of work called flow work is associated with flowing systems. Okay, so that's the new element which we have introduced here. So again, if you want to think about energy of a flowing system, you can contrast that with the energy of a non-flowing system. So these are the terms which you have already seen. There's internal energy, that's the kinetic energy of the center of mass, and the potential energy of the center of mass. On top of that, we have this flow work incorporated. That would be this term, the same as this term here, and all the other terms remains the same. Okay, so if you notice, this and this put together is actually enthalpy. H is equal to U plus PV, right? We had defined enthalpy in the previous few lectures. So these two put together gives you enthalpy. Okay, so enthalpy is of great utility when you're thinking about flow systems. So continuing on, if you want to do the overall energy transport, the quantitative expression is that the energy transported by the mass that is coming in is equal to mass times, let's say if you're thinking about per unit mass, so that is theta, let's say. So see, if you look at this is kilojoules per kg. Okay, that is the specific energy. And then you multiply that by total amount of mass. So this is an expression which we saw in the previous slide, right? These two you already know. This is just PV plus internal energy. So per unit time, if you know the mass flow rate, you can know the energy transport, okay, per unit time. Okay, so that is given by mass flow rate times energy per unit mass, right? So that is the way to compute the overall energy that is transported into the control volume, right? So this is the energy that is brought in because of the fluid that is flowing into this control volume. Okay? So most of the engineering system operate at steady state. Here there's a power plant. So typically there might be an unsteady state which has to do with startup and shutdown. Okay, so that might be a very a small fraction. Most of the time, the power plants are operating at steady state, and typically the time it operates in the unsteady state regime is associated with startup and shutdown. That's typically not so much. Okay, so you should know how to implement first law of thermodynamics to steady flow systems. So a complex system, we abstract it into a simpler, more analyzable system. So we define something like a control mass. For a steady state system, the energy that is in the control mass, control volume, is not changing. The mass within the control volume is not also changing, right? So because the volume of the control mass is not changing, the boundary work is zero, right? So because the control volume is a constant. So for typically steady state system, even though there are property variation within the system, okay, there can be a spatial variation, but at a given instant, the time rate of change of these properties is zero. Okay, so they are not changing with respect to time. There can be variation of properties across the control volume. There can be spatial variation, but there's no time variation. Okay, so variation with respect to time. So for all these steady state analysis, the mass flow rate remains the same. Associated with the flowing mass is some specific enthalpy of the inlet and the outlet streams, right? So that's the way we are going to define our steady state system. There is no variation with respect to time. So if we want to implement it further with more detailed expressions, you can also have other interactions like the heat interactions and work interaction. So here again, we are doing steady state balances. So for steady state system, the mass that is flowing in is the same as the net, the time rate of mass that is flowing in is the same as time rate of mass that is flowing out. Okay, so this is true. Associated with this is the rate of energy, net energy transfer into the system that can occur by three ways, right? So you're already familiar with heat and work interactions. In addition to that, in these flowing system, there is mass that is flowing in. That can also bring in energy. For the system that are operating at steady state, the rate of energy transferred in because of these three ways of energy transfer, heat transfer, work transfer, as well as the energy that is transferred into the system because of the mass flow rate of the system, as it is operating in steady state, this is equal to the rate of energy that is transferred out of the system via these three means, heat, work, and mass flowing out of the system. So that's what we have implemented here. The net rate of heat transfer, net rate of work transfer, net rate of energy transfer because of the mass rate of fluid that is flowing in is equal to energy that is transferred out. So this term is what we saw in the previous lecture, can be elaborated further as energy of the center of mass, kinetic energy of the center of mass, potential energy of the center of mass. This is the U plus flow work, which comes out as enthalpy, right? So this is the overall net rate of energy that is transferred in. This is the net rate of energy that is transferred out of the system. So if you want to express the first law of thermodynamics for flowing system, the expression is as follows. Okay, so there are few new terms. All these terms are incorporated via using this enthalpy. Okay, so this is already what we saw for a closed system. So for a flow system, this remains the same. These are the terms that go that have to be taken into account for a flow system. So let's understand one specific part here, one particular term, this work term. What do these terms involve? Okay, so for things that are operating at steady state, for example, there is no boundary work, as I already mentioned. The flow work is already incorporated within enthalpy. Okay, so what does this term really involve? This term will involve aspects of electrical work, aspects of shaft work, okay? Net rate of electrical work into the system or out of the system, and shaft work, okay? So these are the kinds of work that are involved. For a steady state system, boundary work is zero, flow work is incorporated into this particular term. So for most of the system which we were going to look at, if you look at the quantitative magnitude, this might not be an important term. The difference between this term and this term might be insignificant, might not be significant compared to all other terms. The same thing applies to this term. There is not much change in potential energy of the center of mass. So these can be neglected. Okay, this and this, these two terms, differences between these two terms can be neglected. So a simplification that is often used for analyzing flow systems is that this kind of an expression. Okay, so the first law expression for a flow system, Q minus W, for a closed system, we saw it on the right-hand side, you would have seen internal energy. But for a flow system, the term that is relevant is enthalpy, difference in enthalpy. The heat interaction and the work interaction add to changes in enthalpy. Okay, so now on top of internal energy, there is flow work that has been added into to define enthalpy here. So where do we go from here? So we have provided the mathematical quantitative framework within the first law of thermodynamics on how to analyze flow devices. In the next lecture, we will look at specific engineering flow devices that operate at steady state. Thank you.